Okay, now we are recording. So I'm going to show you some slides for a bit, and then we will come back to the view here in the lab, and that will be the playtime portion of the presentation. So come on. Okay. All right. So good morning. Welcome, everyone. Today we are going to talk about conducted susceptibility to transients in the time domain, focusing on the CS06 method. I'll also be talking about some other equivalent test methods, but they're all basically related to CS06. So can everyone see the charts, by the way?
Yeah, we do.
All right. So here are the topics that I'm going to be talking about. I will say here that much of the material in this presentation is taken, and I'll call it recommended reading, is taken from Gev's application note that I wrote with Jen Dimoff, specifically about CS06. And I will provide that app note. It's already actually up on the Teams page. There is already a folder for Gevs and for application notes, but I'll put that application note in the folder for this session so that you can have access to that and read it if you'd like. So it goes into a lot more of the gory details about transients and the math that I know and love. So anyway, so for the guys here in the lab, I'm hoping you can actually see this reasonably well. But so since I'm in this foyer area, I don't have the big screen TV for the guys who are here in person to see, but we'll get by. Okay, so we'll talk a little bit about conducted transients on the power bus. As you know, I'm hearing a hot mic, so can you mute if you're not asking a question, please? I always like to understand what is it we're protecting ourselves against. I mean, just pumping your hardware with the CS06 pulse, that's all well and good, but you should have some understanding of what it's representing. So we go to our basic model of power distribution here. You have a power subsystem, some common source impedance, your distribution point, and then you have your loads hanging off of that common distribution point. Well, transients on the primary power bus will result from equipment being switched on and off the bus. A turn on transient, when you flip the switch and turn a load onto the bus, will tend to generate a negative going pulse. And a turn off transient, when you open the switch, will tend to generate a positive going pulse. And we'll talk a little bit more about that here presently. And so those will produce transients at the common distribution point that will be seen by all loads. So that's why you care about this. From a susceptibility standpoint, you're some other load, call yourself load 2, while load 1 is being switched on and off the bus. So when you're talking about CS06, you are load 2. You are some other load that's just out there operating, minding your own business, but some other load is being switched on or off the bus, generating these transients. So for our common source impedance model, I'm going to start with our Lisen model that we've discussed in previous sessions. But it consists of just the series resistance of your conductors. I'm calling it the distribution. That's what the sub D means. So the distribution resistance, then the inductance of that wiring, L sub D, and then the characteristic impedance of that wiring that's getting you from your power source to the distribution point. So just C naught. I'll talk a bit more about the more of the physical representation of that. We're going to start with the Lisen model just for simplicity. And then I'm just going to represent a typical load with a capacitance and then just some resistance in shunt. Clearly, real loads are a little more complicated than this, but generally speaking, I mean, this is a power input, so there's generally some filter bank dominated, or filter dominated by a capacitor bank. So this is the basic load representation I'm going to use to illustrate the general concept here. So we'll take that source impedance, the Lisen model, connect it up to our load through a switch. And so when the switch is closed at what we'll call t equals 0, well, at that instant, the load capacitance is going to momentarily look like a short circuit. So one of the things I always like to say, well, and it's just factual, it's physics. You cannot change the potential across a capacitor instantaneously. You can change the current instantaneously, but not the potential. So when you flip the switch, it's kind of another way of saying the same thing. It looks like a short circuit at that instant. So it's going to pull as much current at that instant as your drive circuit can source right at that instant. Okay. But then after that, oh, sorry, getting ahead of myself. So what that means is that your distribution potential, the voltage at the distribution point, is going to be momentarily pulled. It's going to be momentarily pulled to 0 volts. And it's going to pull it to your reference here to 0 volts. Then for t greater than 0, now that the switch is closed, well, now the capacitor is going to charge up, and your distribution potential, V sub D, will increase to the bus potential per the time constant. So that's going to be approximately the square root of your LC time constant, the L sub D and the load capacitance, if the inductance dominates. Or if this load resistance dominates, it'll be closer to your RC time constant. But one way or another, it's gonna be pulled instantaneously down to 0 volts or close to it, and then ramp up to the bus potential according to the time constant of the circuit. Now, in that CS06 application note, I go through all the circuit analysis and the math, and it's complicated relationship. How much damping are you getting from this load resistance and all that stuff? If it's underdamped, you're gonna have ringing. All that stuff you can read to your heart's content, but this is the basic idea. And remember, I mean, this is our distribution point, so we're hanging other loads off of this point, so this transient will be observed by all of the other loads on the bus. So that's why we care about it. Okay, if this was the only load on the bus, then there wouldn't really be any particular problem. But it's putting this stuff on at this point that everybody else is going to see. All right, so for a turn off transient, the switch is still closed. So, you've reached steady state. Your load is just humming along, fat, dumb, and happy, drawing whatever DC current it needs. This is assuming a DC bus. The general case applies to, 120 volt AC or just any AC power bus as well. But we generally are dealing with DC power. But you're humming along with whatever steady state power and current you're drawing. And so, but the thing to note here is that you've got that load current is flowing through the source inductance. Okay, so remember what I said, that you cannot change the potential across a capacitor instantaneously, but you can change the current. Well, with an inductor, it's the reverse. You cannot change the current instantaneously through inductance. It doesn't like that, but you can change the voltage instantaneously across it, and the voltage will change to whatever it needs to be to keep that current flowing at the instant that you open the switch, which is the very point we're getting at here. So if we throw the switch open at, again, what we'll call t equals 0, that current is still going to be flowing through that common source, that source impedance, or dominated by that inductance. And that current is going to will keep flowing through whatever impedances it can find. And this is what we call inductive kickback. That's really exactly what it is. When you've thrown open a switch or opened up an inductive load, you can consider this source impedance a load here, but you've opened up the path for a current flowing through an inductor, and that current still has to flow somewhere. It will flow somewhere. It will act as a current source for that instant. And in this simplified model, the impedance it's going to find is the Z naught, the characteristic impedance of your Lisen. We'll talk about the more physical ramifications of this here in a moment. But this just provides an easy visual to understand that current has to flow somewhere. By the way, I didn't throw in a diagram. Maybe I should. But seasoned analog electronics designers, you know that this is precisely why we put diodes across inductors, so that in a situation like this, that current will flow through the diode until the field collapses and the energy dissipates, and it does it in a nice controlled manner when it's done properly. That's exactly why we do that. So when you see diodes across inductors, if you're not familiar with that, that's precisely why. Okay. So that current now is going to flow primarily through this impedance here. If ideally, as we've represented it here, that's the only path. So the VD, the distribution potential, will increase momentarily to that load current IL times Z naught times that characteristic impedance, right? Just V equals IZ. And then it will decrease back to the bus potential per the L over R, or in this case, L over Z naught time constant. Okay, so that's what gives you a sharp positive going transient, that initial inductive kickback of that current finding some impedance, and it's going to drive this potential to whatever it needs to be to keep that current flowing until the field starts to collapse in the inductor. Okay, so it's just going to be whatever that starting current is times the impedance it finds. So that gives you this big spike here, and then it will just, as the field dissipates, that potential will decrease back to the bus potential according to the L over Z naught time constant. And again, that transient will be observed by all of the other loads on the bus. So that's why we care about this from a susceptibility standpoint. Now, looking more at the physical model, and again, this is very simplified, but I think it gets the point across. Your common source impedance really doesn't have a physical resistor for your Z naught, for your characteristic impedance. It's going to basically be some sort of transmission line getting you from the power source to the distribution point, whatever that wiring looks like, whether it's traces on a circuit board or physical wires going to bus bars, whatever it is, there's some kind of wiring or conductors getting you from the power source, represented by V bus and return, to the distribution point. So it's going to have some characteristic impedance, which is formed by the transmission line parameters of inductance and capacitance, which we've discussed in previous sessions. So this is more the physical representation of, or the physical manifestation of, characteristic impedance. And again, just from basic transmission line theory, Z naught, the characteristic impedance of a transmission line, is the square root of L over C. In this case, L sub D over C sub D, just the distribution, inductance, and capacitance. And the time constant of an LC circuit is the square root of LC. Okay, so we look at this again in this light. Well, so again, when T is, before we throw the switch, right? So T less than 0, the switch is still closed. We're still in our steady state. Well, we have that load current is flowing through our source inductance still, right? If it's steady state current, basically all that current's flowing through the inductance. Now we throw the switch at T equals 0, and here again, that current's is still going to flow through that inductance through whatever path it can find. And if all that's there is this distribution capacitance, that's where it's going to go. And so your VD will now increase momentarily to still IL times your Z naught times your characteristic impedance, but that equals the square root of L over C. and that's derived in that CS06 app note. So again, you can read the app note if you want to go through the math and the derivation if you like that sort of thing. If you're one of the handful of other people in the world that like that shit as much as I do. But anyway, and then it will decrease back to the bus potential per the time constant. So the time constant being square root of LC. So gets you to the same basic transient, but just giving you a little more of an idea of how this happens physically, as opposed to with that Lisen model with a physical resistor representing Z naught. Okay. But the thing to note here, what I think is beneficial for looking at it here, when you look at it in terms of actual capacitance as opposed to a Z naught and a Lisen, if you just look at the magnitude of V max, the maximum magnitude of V sub D, so just the maximum magnitude that your spike can reach, it's a function of your starting current. What's the steady state current before you throw the switch, times the square root of L over C. Well, so if C is really large, then that's going to knock down large with respect to the inductance, that is, right? That's going to knock down the maximum potential you can reach. So a large capacitance at the distribution point will minimize the magnitude of the transient that you can achieve in a given power distribution scheme. And this is significant for certainly a lot of our recent in-house programs at Goddard, that are designed by our local power folks who are my neighbors in Building 20. That their distribution point is actually on a printed circuit board inside their power distribution unit, or whatever equivalent name they give it. And they generally put a big honking capacitor bank of several thousand microfarads right at the distribution point. And then they tap off of that point to go to their different loads, to the different connectors on the PDU to go off to their different respective loads. So a lot of these transients are significant factors on distribution schemes that are dominated by inductance. So, if you think of like the distribution in your house, in your building, or like on a military platform, like a large aircraft carrier, which is basically like a building, the distribution for a given circuit, you've got a long pair of wires going from the distribution panel, wherever it is on the vehicle or in the building, to an area of the platform of the building. So say like the area of your building where your office is, all those electrical outlets in that room are probably ganged together. So that common source impedance consists of that long set of wires going back to the distribution point. You have no idea how long it is, tens of meters, maybe 100 meters or more. So there's probably substantial inductance there without a huge amount of capacitance. I mean, you'll have the transmission line capacitance just from that wiring, but that the Z naught of that kind of construction of a transmission line is going to be on the order of 50 ohms, give or take, maybe between 50 and 100 ohms. So what that means is that if you're pulling an amp of load current before you throw the switch, and let's just say your Z naught is 50 ohms, well, you could have a spike of 50 volts. I mean, very easily. And if your starting current is even higher, and if your characteristic impedance is maybe pushing 100 ohms, it's not too hard to see that you could have transients of a couple hundred a couple hundred volts. So when you see this stuff about a transient of 200 volts, and you think that's ridiculous, how could we possibly have that on a 30-volt bus? You can very easily, if it's dominated by inductance. Okay, but on a spacecraft or any kind of platform where you can run your loads, the leads going to your loads to a common distribution point inside a PDU, and put a big honking capacitor bank at that distribution point, put several thousand microfarads there, which is what they've done. 6,000 microfarads plus is what they tell me. Then your Z naught, your L over C is now very small. And so even pulling several amps here, if your Z naught is less than an ohm, you're not going to get much of a transient here. So it's important to understand that about your platform. Again, my mantra: know thy platform. Because if you have a platform like that, where if your power distribution is designed like this, with a big capacitor bank at the distribution point, transients are not likely to be a significant problem. Okay, and so here's the summary. Everything here. So a large capacitance, again on the order of thousands of microfarads at the distribution point, will drastically minimize the magnitude of positive going pulses resulting from turn-off transients. And it stands to reason, and I've got details, again, for the interested reader in that CS06 app note. It's also going to minimize the magnitude of negative pulses resulting from turn-on transients. I mean, just looking at it heuristically, going back to this diagram, if you got a big capacitance here, especially if this is large with respect to your load capacitance, then the energy that it takes to charge up this capacitor is going to come largely from this capacitance here, and it can absorb that energy, and you might get a little bit of a dip in the bus potential here, but certainly not going down to 0 volts, right? And so it's important to understand that if the largest dip that you can expect to see on your platform is on the order of half a volt, then it doesn't necessarily make sense to test your hardware with transients going down to 0 volts. Right. So, and this underscores the point I just made. Work with your power subsystem designers as early as possible to understand the power subsystem architecture and determine, are transients even a significant concern on the platform? I mean, if not, CS06 or an equivalent test really doesn't need to be applied. We did not apply it on RST for that reason, because that's an in-house program. It has the kind of architecture I just described, and worked with the power team early on. They did some analyses and said, yeah, these kind of transients are not going to be a significant concern. But if they are to be expected on the power bus, you want to know what are some reasonable upper bounds. Okay. And we'll talk about some of the default limits in the mill standard, so that you can apply some of that engineering judgment instead of just applying some of these default levels. So again, further reading is that CS06 app note that I'll make available in the folder when I post the video and these charts. Okay, anybody have any questions so far? Now we're going to talk about the CS06 test method and equivalent.
So are you going to discuss like having a short on the bus, a transient short and fuse and that kind of thing?
Well, that's one of the things that can cause this. I mean, sure, we can go back to this for a second. Yeah, if we could, this is fine right here. So I've been putting this in terms of an actual physical switch, whether it's a FET switch or a relay or whatever, like an intentional command to open up that load, right? That's what I've been putting it in terms of. But
Yeah.
That's Mike, right?
Yep.
Yeah. Yeah. So what Mike is saying is, well, what if you got a fuse? And what if you've got a short in the load that pops the fuse? Well, it's basically the same. It will have the same effect, right? Obviously, the cause is different, right? But between an intentional command to open a switch versus popping a fuse. So yeah, what I haven't really shown here is there's generally a fuse in series with the switch, right? But you pop the switch, well, you got something that open circuits your load very quickly, and so it'll basically be the same type of thing. In fact, I think the first time I heard about these kind of transients was in the context of a fuse blowing. And then it turned out we already were applying CS06, and it turned out, okay, we don't really need a separate requirement saying you shall survive a fuse blow that produces this kind of transient on the bus with these characteristics. We're like, we've already got CS06 that encompasses that. We're good with that. We don't need a separate requirement that says the same thing. So does that answer your question, Mike?
Yeah, but it's to an extent because it's initially a short and then it's a open, right? So there's a
Oh, yeah,
two-phased
okay, I see what you're saying. Yeah,
event.
right. You kind of get both. You get two transients for the price of one, I guess. Right?
Yeah,
The initial short in the load will, let's go back here. Your initial short in the load will sorry, it jumps over all these animations. There we go. So your initial short will give you something like that. And then when the fuse pops, then you'll get the positive going one. So yeah, I mean, you'd have to look at the power subsystem architecture to see what's the worst case that can happen on the bus when that happens, right? But
yeah.
but that's how you would want to set your CS06 limits to make sure you're encompassing that properly. But I would think that you're basically just going to get, you know, a negative going transient immediately followed by a positive one.
Thank you.
Okay.
And that's
All
up
right.
to whoever's designing the power supply to do that kind of an analysis for the
Correct.
CS06
Yes.
type transient assessment. Thanks.
Yep. All right. So any other questions before we shift gears? This is all just like the nature of transients on the power bus. Now we're going to talk about how do you test for them. Okay, well, with that, I'm going to move along. So here is the CS06 limit from the original version of Mill Standard 461 from the Summer of Love in 1967. And basically it was unchanged in 461A from, I believe, a year or so later. But this is way back before CAD, where they actually hand drew these curves on graph paper. And it's very hard to see, so I've annotated this. It's a 10 microsecond pulse, okay? And positive and negative transients are applied. When we get to the test equipment here, you basically you physically reverse the polarity of your connection to the generator, right? But you want to apply positive and negative transients, as we've discussed. And then the default here that you can barely read, which is why I rewrote it here, it's 2 times the line voltage or 100 volts, whichever is less. Okay, so just going by this default, even if you're going on a 28 volt, or we'll call it a 30 volt DC bus, this is telling you, well, that you'd want to go 2 times the line voltage, so up to 60 volts. So that means that your negative going transient is going to pull you down to minus 30 volts. This is something that gets very confusing. But if you just think about, you know, when the way the magnitude of the transient is defined, just think of it as the magnitude of the transient. So if the magnitude of the transient is 2 times the line voltage, then the negative transient is going to pull you down to minus V bus. So if it's a 30 volt bus, it's going to pull you down to minus 30 volts. And then the positive transient, it's going to be 60 volts on top of the 30. So it's going to take you up to 90 volts. Now, we don't generally do that, but sit tight on that. I'm just saying this is the default in the original version of the Mill Standard. So then when they went to version B in sometime in the 70s, I believe. I forget the date off the top of my head. They added a 150 nanosecond, or they call it 0.15 microsecond spike. Okay, the basic shape is the same. Yeah, it's still a 10 microsecond pulse is the primary one. They added the 150 nanosecond pulse, but here the magnitude for the 10 microsecond spike is 200 volts. You know, they just say 200 volts, and then for the 150 nanosecond spike, it's 100 volts. Okay, so then we go to mil standard 461C. They still have both the 10 microsecond and 0.15 microsecond spikes. Well, now they've increased the magnitude of the 0.15 microsecond spike to 200 volts, so the same as the first spike. And then in the test method specified in mil standard 462, they actually only specify the 10 microsecond pulse. For whatever reason, I couldn't answer why that's the case, but that's the default is the 10 microsecond pulse, and they specify a repetition rate of 3 to 10 pulses per second, for whatever that's worth. Okay. So now, in the test method, in mil standard 462, it specifies the test method. Remember in 461F, or I'm sorry, E, and later they incorporated the test methods into 461, so it's all in one document now. But way back when, 462 is a separate document that specified the test methods. 461 was limits only. So there are two basic setups here. There's the series injection, which they specify for AC powered lines. And so you put the spike generator in series with the power feed. So it's much like CS101. Or there's parallel injection specified for DC powered lines. Okay, now if you go with the parallel injection method, which I don't like, but here we are, you need to put in an inductor, and this was not in the original version of the mil standard, I don't believe. I think this came with one of the later versions of mil standard 462. When they realized that if you just try to put your spike generator here without anything in between, and with whatever capacitance your power source has, that's going to load down your signal source. So you need to put in this 20 microhenry inductor to give you some isolation between the signal you're trying to isolate from an AC standpoint, that is, right? So that you can inject the signal that you want here without your power source loading it down too much. But that means this is a different configuration from pretty much everything else that you're doing with the standard setup that we use for at least the GEV's modified version of mil standard 461 based testing. So so I'm not in favor of this method. So
hey John,
yeah.
This is Ed. Yeah, so yeah, with the series inductor, it looks like you could run yourself afoul of source impedance. I mean, the running, stability of your converter, right?
Yeah.
You would not satisfy the Middlebrook criterion.
Yeah, that's entirely possible. Yeah. So just the series method by comparison. I mean, it's the hardware setup is pretty much the same as CS101. It's just a different signal source, right? It's a spike generator instead of a sinusoid. But here they're just showing this notional capacitance here. But for the GEV setup, we have the GEV's capacitor network that we use. You can just leave that in place. You don't have to mess with it. Right. But it is recommended you take this out if you do the parallel injection method. So it's not just adding the inductor, it's removing the capacitors. But if you do the series method, you leave the capacitors in. It's basically the same setup, just in putting your signal source in series with the power feed. It's similar to CS101, similar setup and teardown times. And I don't get too hung up on AC power leads. You can do this on DC power leads. It's just fine. And we've done it successfully many times. So nothing's stopping you from doing the parallel injection technique if you really feel strongly about it. It's just, you know, if I'm in charge of the test campaign, we're doing series injection. And with any signal injection test method, there's a pre-calibration step, surprise. And this is calibrated across a 5 ohm load resistance. CS101 is calibrated across a 0.5 ohm. So you just got to pay attention to that. You know, different resistor, but then it needs to be a power resistor because you're putting a fairly hefty amount of signal through it. It is just a spike, so it's a little bit different from putting that amount of energy through it continuously. But still, you don't want to be using a 1/4 watt resistor for this. And we'll get to this here in just a moment when we get to playtime. Okay, so now there's this CS106 that I put in quotes because there's another CS106 that I'm going to talk about that's different from this. So we got to just be very careful which one we're dealing with. This one was defined first for the space shuttle program in this SLE triple ball 2 document. And for the power distribution scheme on the shuttle, they did not did not see any significant risk of positive going transients, so they did not apply a positive going pulse. They only applied this negative going pulse for equipment being turned on to the bus. And some of those negative going transients they expected could be as much as 100 pulse widths of as much as 100 microseconds. So that's what they defined. And so there we go. This is not something, I mean, space shuttle program is no more, so there's no reason to apply this. I believe they made a dedicated pulse generator for this, or you might have had to make your own, whatever the case may be. But you don't really have to worry about this anymore. I just put it in here for context. Now there's the more official CS106 that was introduced in Mil Standard 461F. But look at some of these things. It's the same basic pulse shape, but the magnitude is 400 volts. Now it says can be tailored, but the default is 400 volts because that's what was expected on, or you know, is expected that you could have transients of that magnitude on Navy ships. And it says right here is applicable to submarine and surface ship equipment. Right, so this was driven by the Navy. They put this in here because it's a military standard, right? It's what mil standard means. So the Navy had this put in here specifically to address concerns that they had on submarines and surface ships. Now the pulse width was now made to 5 microseconds, so it's shorter than the CS06 pulse, right? And the test method, they only specify series injection, which I think is rather interesting. But that's the only diagram in the mil standard, at least that I recall. So, but in the application guide for mil standard 461F, it says the primary concern is to ensure that equipment performance is not degraded from voltage transients experienced on shipboard power systems, coupling to interface wiring inside enclosures. Right? This is an important point going to the next slide. This wasn't really intended to evaluate susceptibility of your power of your load of like your power converter itself. It was intended to evaluate potential crosstalk to interface wiring inside enclosures. So with that, we go to mil standard 461G. Well, it gets rid of CS106. It is no more. All right. And just reading the highlighted bits here, the underlying issue was not the response of the power supply to the transient, but crosstalk within an equipment. Interesting wording, within an equipment between the transient on the power wiring and the signals carried on wiring adjacent to the power wires without adequate protection. The purpose of the requirement was to force adequate segregation between power and signal circuitry. So I recall discussing this with Ken Jabor some years ago, where I think on some of these Navy platforms, they would combine power and signal wiring in a given cable and going to a common connector. And I think that was the concern that they were trying to address here. So and this is all verbatim right out of the 461G appendix, says it was concluded that CS115 and 116 already meet the intent behind the reintroduction of CS106. So they got rid of CS106 in Mil Standard 461G. It is no more. So sometimes I see people put in test plans that they want to do CS106 as some, I think maybe some desire to appear to have consistent nomenclature with Mil Standard 461G based tests. Please don't do that. If you're doing CS106 and you're applying a 10 microsecond pulse, please don't do that. CS106 means a 5 microsecond pulse, and there's no reason to apply it. So if you're going to apply a pulse, I mean, this is getting to Gibbs. So when we addressed, okay, if we're going to do anything in Gibbs, well, we'll apply a 10 microsecond pulse. I'm going to talk about these signal generators here coming up, and then we'll get to playtime, I promise. But where CS106, came and went with one version of the Mil Standard, you basically, at least for a time, you had to buy a dedicated signal generator to get that 5 microsecond pulse. I mean, you see that these are kind of unique pulses. I shouldn't say they're terribly unique, but you generally buy a dedicated signal generator to give you that pulse shape, right? And for a time, the default CS06 pulse generator only gave you a 10 microsecond pulse. And then CS106 came along and it only gave you a 5 microsecond pulse. And then 461G said, oh, never mind, we're not going to apply CS106 anymore. So to force people to possibly go onto eBay to find an obsolete pulse generator to get that 5 microsecond pulse didn't really strike me as being time well spent. It's really the pulse width that's going to be a worst case here, right? You can generally, like a very, very short pulse, like nanoseconds, you could probably deal with hundreds of volts, no problem. But a much lower magnitude, but a wider pulse is more of a concern. That's a harder thing to filter, right? So we just said, well, let's just go with the 10 microsecond pulse. So if people, for any labs that own only one of these older CS06 generators that only gives you 10 microseconds, we're not making people buy any new test equipment. Okay. So we're applying a 10 microsecond pulse just so that you can use a CS06 generator, and it's 100% of bus potential, right? So the default is that we apply the negative going pulse to take you from VBus down VBus to 0, right? And then we apply series injection. Again, if you're running a test campaign and I'm not there, if you really prefer parallel injection, I can't stop you, but I still believe series injection is much handier and just a better method, but there we go. Just highlight here, the pulse shall be applied a minimum of once per second for 1 minute. Okay, so 1 pulse per second. The repetition rate, there's nothing particularly magical about it. You could go up to 10 pulses per second for all I care, but one pulse per second is generally sufficient. These transients are not something that is happening, at a kilohertz. These are happening once, very occasionally throughout the mission, ideally, right, as you're turning equipment on or off. So once per second for 1 minute, it should be more than sufficient. And then for all platforms, the negative transient shall be applied. For platforms that include rapidly changing inductive loads that are expected to generate significant back EMF onto the bus, the positive transient shall be applied as well. So that's where your mileage may vary, right? Again, know thy platform. If your power system designers, do their analysis and determine that transients are just not going to be a significant problem on your bus, then you really don't need to apply this. But if you can't completely make the problem go away, or you can't convince yourself that there will be no transients to speak of, but your turn on transients might take you down to half of bus potential, right? So from 30 down to 15 volts, then okay, apply the negative going transient to half of bus potential if you've done the engineering work to justify that makes sense. Okay. Right. Now we'll talk about signal generators, and I've got a couple of these sitting here, but I'll highlight a few things, and then we'll actually show you some stuff. So this is the old Solar 6284-5S. Specific, I mean, it really is specific to CS06. You see that there's the parallel injection output on the left, series injection on the right, and this gives you only a 10 microsecond pulse. And the controls basically are repetition rate and amplitude. And I have one of these sitting here. I'm not really going to bother using this unless anybody really feels strongly about seeing it. We can see everything we need to with one of these other ones, which will come up in just a moment. Here's just the spec sheet for that signal generator. It really just highlighting, it is designed specifically and exclusively to give you that CS06 pulse. That is its raison d'etre, its purpose in life. So like no more, no less. Now this is the 2854, also by Solar, CS106 generator, and its whole raison d'etre mission in life is to give you a 5 microsecond pulse. Basically the same shape, just the pulse width is 5 microseconds. So here again, this machine, this generator was built specifically to do CS106 testing that is no longer applied. I mean, at least per 461G and later. There may well be some military platforms that still can insist on doing this. That's beyond my control. But there's no reason to ask anybody to go buy one of these things. I'm just providing this for context. But that brings us to the Solar 8282-1. That's the one that we're actually going to play with here in just a moment. Here again, you got parallel injection series and series outputs. This gives you all three: the 150 nanosecond, the 10 microsecond is the biggie, but it also gives you the 5 microsecond. Just buttons right here on the front. So you could get the 5 microsecond pulse if you want to, but if you've got one of these machines and you really want to test susceptibility to transients, I would recommend the 10 microsecond pulse. That's going to give you a worst case. Now, some platforms, in fact, the reason that this whole session was requested is that there is a project that is requesting to do CS06 or to do transient testing, and they want to apply both the 10 microsecond and the 150 nanosecond pulses. So for whatever that's worth, and we'll show you that here. I think maybe right now. Yes, it is playtime. Does anybody have any questions before we play? Okay, you're all just antsy to play then. So, all right, let me stop sharing the charts. So can you see the view in the lab now?
Yes.
Okay, so I may pick up the camera and move it around here in a little bit, but the basic setup, we're not going to actually hook up to the unit under test in the other room. This is all just the pre-calibration setup, but I say this for all conducted or any kind of susceptibility injection test. Don't understate the importance of the pre-calibration step. It is extremely important. That's where you're characterizing what it is you're injecting. Once you inject into the EUT, you don't really know what the impedance characteristics. Wait, I'm seeing a note looking at my laptop right now.
Sorry, I was making a joke.
Humor. Was that? I have to go back and watch Good Morning Vietnam at some point because one of my favorite lines that I always butcher, but it's the guy who says, "Humor is one of my hobbies." Saying that to Robin Williams' character. But anyway, so anyway, back to what I was focus. All right. So what's that? Calibration. Yes, thank you. Dependra's keeping me honest here. So yeah, the calibration step is when you are injecting into a known load, and that is your opportunity to characterize your injecting signal. When you go into the equipment under test, that's a less controlled environment, right? You don't know what the impedance is of your EUT unless you've specifically characterized it. And you do want to monitor the signal that you're injecting, but you're going to have less control over what it looks like depending on the impedance of the EUT at any given frequency. So the pre-calibration step, is extremely important. If any equipment provider is pressuring you to, oh, why are you doing this pre-calibration? Let's just get on with the test. You need to impress upon them that's every bit as important as the test itself. It's like, when you stop to get gas before a road trip and somebody tells you, oh, don't bother with that, let's just hit the road. Even if you can hear your fuel pump sucking fumes, right? Don't do that. Put gas in the car and then go. That's probably a terrible analogy, but I'm going to go with that. Okay, so here is the 8282-1. That's the main, probably the only one that I'm actually going to demonstrate. This is an identical unit. I did check them out. I guess it was a week before last. They do pretty much behave identically, so there's no particular reason to show them both. We were seeing a few strange things. In fact, I'll show you the strange things we were seeing with this unit, but then we were seeing the same stuff here, and then we figured out why. So this is basically just here for show and tell. So we have two of these model 8282s. You can't quite see over here. That's the 6254-5. That's the older model that gives you only the 10 microsecond pulse. So I did hook that up week before last, and it does give you essentially the same pulse shape as what we're going to see from the 8282. So I'm just going to concentrate on the 8282 here. So at this point, I'm going with the series output. The main difference, I believe, is that the series output almost certainly has a transformer inside. There's very likely a transformer inside this. Probably very similar to the CS101 transformer. I've actually sometimes seen people connect through their CS101 transformer. I've seen people do that. There's no particular reason to. If you use the series output, you've already got a transformer in there. The parallel output probably just has an AC coupling capacitor or something in there. But the wave shapes do look the same out of both outputs. So I'm just going to look at the series output. And so we're going from the output, pair of banana leads, to a 5 ohm resistor. This is a whole bank of resistors we use for different things. But the one I'm hooked up to, say 5 ohms on it. I can't quite read the power rating on this, but you can see these are power resistors. It's probably easily 100 watts. That may even be 200, 50 minimum. And you see it's on a nice big heat sink. So, that's the sort of thing that you want to do with these calibrations. It's much more important with CS101 because when you're going into a half an ohm, you're putting a fair amount of current in there, and that's more steady state. So the resistor is going to get hotter more than likely with CS101. But even still, when you're putting 30 volts or more across, or if you actually go with some of those defaults and you're putting 200 volts across a 5 ohm resistor, you want it to be able to dissipate a fair amount of power. So,
hey, John,
yes, sir.
Did you verify? I know we were disconnecting and reusing some of the resistors either Thursday or Friday last week. Did you double check to make sure all of them are connected how you need them?
Yeah, I
Okay,
set
wanted
that
to make
beforehand.
sure before you
Yeah.
turned it.
Yeah, I did that beforehand.
Got it.
Yeah. I don't generally like doing things for the first time in front of a live studio
Yeah,
audience.
I know we were fiddling with we needed one resistor for something else last week, so I just wanted to make sure it was
Yeah,
kosher.
yeah, it's kosher. So yeah, we're going, we have our pair of banana jacks going across our 5 ohm resistor, and then we're using a differential scope probe. For this, you probably could get by with a single-ended scope probe, but I've gotten very accustomed to using differential scope probes, and that is my preference if one is available. For your pre-calibration step, it probably doesn't matter, but when you're injecting into the UT, the differential probe really is more important. You don't want, the connection, your reference connection going through your scope into facility ground and all that stuff. You don't want that to perturb your configuration, right? Which it can. So we got a differential, and this is, we're dealing with high voltages here. So this is specifically a high voltage differential probe. So there we go. So I'm going to go ahead and turn this on. These generators don't have an enable switch. So when you power them on, they're on. Okay. So I have already set up the amplitude. You probably, well, all right, let's do it properly. I'll turn the amplitude down. So we'll turn it on, and it's set for 10 microseconds. This set of switches here, you move this in. This is just setting the multiplier for your repetition rate. This first one's just ×1, and then this is where you're actually setting your repetition rate. So it's just set for 1 and ×1, so just 1 pulse per second. And then the next one over is PPS ×10. So if I just hit this switch, it'll go from 1 pulse per second to 10. So anyway, this is pretty much the standard pulse generator at this point. I mean, this one used to be when all we were worried about was a 10 microsecond pulse. So if you're going to be doing CS06, you're probably going to be using this, whether it's in your own test lab or any test lab that you've hired to do your test. So that's pretty much it. That's kind of one of the things I like about these older pieces of test equipment is there's not that much to it. There's not some sick memory scheme or touch screen or anything like that makes you swear at it for 10 minutes before you can get it to do what you want. You turn it on and it works. So I'm a soon to be retired guy, and I can talk like an old curmudgeon if I want to. So thing is, it's not just old retired guys who talk like that. My daughter's actually said that recently. Like, I don't need an app to do everything. Anyways, moving right along. So, all right. So I'm gonna take this off of the stand and go over here. So can you see the scope? I have to readjust myself here so I can point at the scope and reach the generator. All right. So can everyone see the scope?
Yeah, we do.
All right. So it may well be rather blurry here, but we're at 10 volts per division and 10 microseconds per horizontal division. So I'm going to start to bring up the amplitude, and it comes up pretty quickly. And 30 volts is a pretty low level. This thing is capable of generating hundreds of volts. So we're at the low end of the scale. So it jumps pretty quickly. So we want 3 divisions at 10 volts per division. So I'm going for 30 volts. So that's about as good as we're going to get. Okay. And so that's our 10 microsecond pulse. And then you get some undershoot. There's not really a whole lot you can do about that. I've seen some of these generators where the undershoot is actually about the same magnitude as the initial pulse. So that gets to Mike's concern where you could basically simulate that kind of double transient just with what's coming out of the generator. But that's basically it. You're getting your 10 microsecond pulse, a little bit undershoot, comes back up to steady state, and that's basically all there is to that. I'm going to move our horizontal scale to 5 microseconds per division. So this is a lovely scope where it goes from 10 to 4. So, anyway, I don't know why they do that. I prefer if it goes 10, 5, and 2, but there we are. So it's 4 microseconds per division. So now we're going to all I'm going to do is press the button to go to a 5 microsecond pulse. And now we have a 5 microsecond pulse. Pretty much the same wave shape. Looks like it takes a little bit longer to get back up to steady state, but what you're concerned about, the real thing that you're defining is that initial pulse. So that's maybe a little closer to 6 microseconds, but that the high precision is not really required here. You see the amplitude has gone down a little bit. There's a little more loss, I guess, for the faster signal. So, okay, we just go adjust the amplitude. Again, it's all manual, it's all knobs. So there we go. We're right basically back up to 30 volts. So all right, so we're going to go to the 150 nanosecond or 0.15 microsecond pulse now. So show of hands, who thinks that we're going to get the nice, same pretty looking signal that we have now? I probably shouldn't be leading the witness. Oh,
Not
one other
me.
thing. What's that?
I'll just say not me.
You've probably already seen this, but one thing that's that is well discovered from just playing, but then we looked in the manual and saw no, they did this on purpose. For whatever reason, the 0.15 microsecond pulse reverses the polarity. And I mean, we saw that when we were just when Rob and I guess Greg and James and I were playing with this a week and a half ago. We saw that, and then we looked in the manual. I was like, no, they did that on purpose, but they didn't explain why. But rather than adjust my trigger or any of that stuff, I'm just gonna actually change the connections here. And I did turn it off first. So, all right. So, all right. So we're still getting a trigger, but I'm still triggering on the positive edge, but it's on this positive edge here. But now let's go to our 150 nanosecond pulse. All right. So it's much more compressed now. So we've got to expand the scale. Ooh. That doesn't look very pretty. Why do you suppose that's happening? And why we didn't see it on the other pulses? Well, source impedance of this generator is about 5 ohms. We're going into 5 ohms. Does this look like a 5 ohm transmission line? No. I mean, it's probably a couple hundred ohms, and it's probably not consistent from one end to the other. Now with the 10 and the 5 microsecond pulses, those are slow enough that it doesn't matter, right? The compared to the rise time of the waveform, this connection is still electrically short. Now that's no longer true. The rise time is, well, whatever it is. If it's a 150 nanosecond pulse, the rise time is probably 10 nanoseconds or less. Right? So it's 40 nanoseconds per division. So yeah, it's less than 10 nanoseconds. This is definitely electrically short. We're getting reflections. Right? This connection is on the order of a meter. So 3 feet foot per nanosecond. About three nanosecond propagation delay. That's comparable to the rising edge that we're trying to achieve there. So so you're definitely seeing multiple reflections here. I mean, we could go through the math and all that stuff, but I think it suffice it to say is we're definitely getting multiple reflections, and we're getting a very ugly waveform here that I'd be reluctant to say I have confidence that I know what I'm injecting into the EUT. All right. So what can we do about this? Eager volunteers? I'd say I hate to put you on the spot, but I don't really hate it at all. Well, one thing we did do, I will confess, full disclosure. One thing we did do when we were playing around with this, I don't remember where the menu is. Oh, we have a mouse. That's right. No, I don't think it's hooked up. Okay, I may not be able to do this. Yeah, all right. No, it's a different mouse. It's just, oh, there it is. Okay. Bandwidth. So this is totally cheating, okay? So don't do this, but I'm just showing you it's tempting to go, oh, let's just, we're at full bandwidth right now. Let's go to 20 megahertz. Okay, that cleans it up a little, and you know, but this is why I don't like bandwidth limiting on the scope, unless you know I'm very cognizant about what I'm doing. Sometimes there is a specific reason, like if you've got a lot of white noise, you know, just a lot of high frequency broadband noise, and you're trying to look at a sinusoid or some signal that's very close to the noise floor, and going to reducing the bandwidth if it's not affecting the signal of concern, you can filter out some of that high frequency noise and get a better read on the signal you're trying to look at. That's all well and good when you're fully aware of what you're doing and why. But here we're actually filtering out some of the signal, and it's cheating. So that's I'm saying, full disclosure, we did this, but let's go back to full bandwidth, because that's really what we should be doing. You should always start on full bandwidth if you can. Just start on full bandwidth, so at least you understand what you're looking at. And then only go to bandwidth reduction on the scope, if it helps you get a little bit of a clearer look at what you're trying to see. But this stuff is real. This ringing is real. And I don't want to filter that out. But the real issue is we've got this uncontrolled transmission line here. It is a transmission line, whether we call it one or not. It's just a very crappy one. So thing to do is improve the connection between our source and the load. Well, fortunately, Solar makes these dedicated resistive loads specifically for that purpose. It's a 5 ohms, I don't know if you can quite see that. It's type 8525, so it's a similar part number. Right? The signal generator is 8282. This is an 8525, and you can order these right off the Solar website. You probably they may even, I don't even remember, these might have even come with the generator. But when you order the generator, you should probably order a couple of these. I think we have 3 of these. I know we have at least one more of these sitting around. But when we were testing this setup out, Rob found these. It's like, well, that's what we should be using. So let's get rid of this crappy transmission line and just plug this directly in. And then we'll move our connections. And remember, for the 150 nanosecond pulse, the polarity is reversed. So positive is going to be on the bottom. Can you hold it for a second? All right, there we go. Thank you. So put the positive connection on the bottom, reference on the top. Now we will try this again. So that's about as good as you can get, right? It's still not ideal, and you also want it to be a non-inductive resistor. It does say that on there. I should have pointed that out.
John, you want to take for the connection?
No, we're fine for now. I don't. Let me look at this real quick. When it says resistive load, I believe on the website it does specifically say that's a non-inductive load. Those resistors may well be wire wound and may have some significant inductance. That's not going to help with with the ringing. Well, it will help with the ringing, just in the wrong way, right? It's going to contribute to the ringing. So you want to use a non-inductive resistor if you can, not a wire wound resistor. And then just, connecting this directly up to these terminals minimizes the connection length and all that stuff. So let's turn it on. We're still set for 0.15 microseconds, 1 pulse per second. And now we have a much stronger pulse. There's less loss in the line, because there isn't a line to speak of. So it's still kind of cruddy, but it's less cruddy. Sorry, I wasn't really pointing at the scope there for a minute. But that's better, and that gets us more to the point of, okay, now we at least have something a little more controlled that we can be confident in connecting up to our EUT. So we're getting our 30 volts, and the horizontal scale, it's this weird 80 nanoseconds instead of 100, but it's looks like a little bit shy of the 150 nanosecond pulse width, but it's close. And probably the ringing is probably affecting that a little bit. But I mean, there's no adjustability on the pulse width. You get what you get, right? So if it's way off, then the signal generator is faulty and you need to have it serviced. But I'm not going to be too concerned that I'm getting 130 nanoseconds instead of 150 or whatever it is. But here we are. That's the basic pulse shape you're getting for the 150 nanoseconds. And the lesson there really is just use that resistor kind of for everything you're doing. Like, even if you're using the 10 microsecond pulse, let's go to that. Now our horizontal scale is whacked, but oh, right, and it's reverse polarity, right? But we can increase the amplitude as needed to get our 30 volts. So then that's pretty much the size of it for pre-calibration.
Hey, John.
Yes.
So if we use if the solar load is used, is there an issue with what the actual transient is applied to the dot? If we have different cabling, wouldn't the ring cause some over or under test?
Yeah, I mean, that's a fair point. I mean, yeah, you're not going to hook your EUT directly up to these terminals. What you might do is let's go back to 150 nanosecond. I don't believe I've ever actually run a test with the 150 nanosecond pulse. To be honest with you, it's pretty much always been 10 microseconds. So I'm learning a little bit on the fly here as well. But
yeah, I certainly have not either. It's always been 5 or 10.
Yeah,
base station requirement.
Yeah. I mean, this is such a short pulse that I mean, any filter capacitors you have in there to deal with CS101 should probably snub out a short pulse like this with no problem. But here we are. If there's a specific requirement or desire to do this, then we should at least be prepared to do it. So, I mean, generally speaking, I'll walk through what we generally do for the 10 microsecond pulse, and then we'll come back to this. So go back to 10 microseconds, and I'm just going to leave it as the negative going pulse. But what we generally do, is this. I'll increase the amplitude to 30, but we take a screenshot, we take pictures of the setup, know that how we've done the calibration. In this case, if we've done it with this resistor packed sitting right there on the generator, and we take a screen capture of this and include it in the test report. So there we go. That's our pre-calibration. Then we hook up to the EUT, and then here's another important point, that you do the pre-calibration, and then you want to inject the same level into the EUT. Well, it's kind of crude how we do that now because of the nature of the equipment, but just here's the display here. This is showing we've got three lights lit on the gauge. And as I said, this goes up to 600 volts. This thing is capable of driving 600 volts, and we're driving 30. And we see each one of those ticks is 10 volts. So 3 ticks for 30 volts. So the way we would do this is, we would put a mark on the dial here. I just put like with a Sharpie or something, or it really is just tape that they've put on here. But you note what level that you've had it set to, and then you would turn it off, connect it up to the EUT, and then similar to CS101, if you're doing the series injection method, you want to turn the generator on before you turn on the EUT. So you'd want to turn this on with the amplitude turned all the way down. So with this thing not having just like an enable switch, you don't want to just, ideally you just want to turn it off without touching the volume. That's the guitar player in me talking. The amplitude knob, it would be ideal if you just switch this off, don't touch anything, hook it up to the UT and turn it back on. But for the same reason with CS101, you want to turn on your drive circuit, your drive, equipment before you turn on the EUT. You want to do that here too, if you're doing the series injection method. Because remember, if you've got a transformer that's hooked up in series with your power feed, until you've actually energized the drive circuit, you've just got the inductance of your secondary of the transformer, which could be millihenries, in series with your power feed. And that's inviting instability and ringing and possible damage when you turn the equipment on. So don't do that. So if you're doing the series injection method, you want to turn on the generator with the amplitude all the way down, turn on the UT, and then when you're ready to test, you turn up the amplitude, and you should be monitoring what you're putting into the UT. By the way, we do that. And but you want to put in the pre-calibrated level, not necessarily adjust until you're getting 30 volts into possibly a low impedance. So it's just a few additional nuances here. But where I was going with this is that if you're doing the 10 microsecond pulse, which is the default, that's what we've generally done. I don't think we've ever even bothered with the 5 microsecond pulse, though you can do it with this machine. But I guess I would be inclined to do this initial pre-cal with the resistor pack. If you're only doing 10 microseconds, then you don't necessarily need to bother with the resistor pack. You could use the wires that you're going to use in the actual connection to the UT. Go to this load resistor for your pre-cal, then just disconnect from the load resistor and then hook up to your setup going to the EUT. Because the 10 microseconds, it's a slow enough pulse that it's not going to be as dependent on the specific interconnections, right? But if you're going to go with the 150 nanoseconds, so let's go back to that. I guess I would be inclined to start with the resistor module, so that now like you're getting the best behaved version of the signal that you can get. Let's take this down. And so with that ringing, you make a judgment call as to what are you going to set the amplitude at. I would be inclined here with that second peak being a little bit higher. I'm going to go ahead and set my 30 volts to, that first peak. I'm going to set that at the 30 volt line. Given a choice between a slight under test or a slight over test, I'm always going to go with a slight over test. I want to know that I've actually stimulated the equipment properly, so that there's no question about it. So anyway, I'd be inclined to get a screen capture of this, take a picture of how I did it, into this resistive load plugged directly into the generator. Then I would hook up over into the resistor because I've got to use some wiring to get over to that. That should be the wiring that I'm going to use to hook up into the EUT circuit. Get another screen capture of that. And if we can go ahead and do that, it takes a second. And with that, with the 150 nanosecond pulse, we're probably going to get some loss. So we might not quite get up to 30 volts without making an adjustment here. Okay, so we're hooked up across the resistor. Then turn this back on. Yeah. Now we're about half the amplitude. So I might be inclined to turn the amplitude up until we're actually seeing our 30 volts again. Now that is doubling the initial amplitude. So there again, you need to make a judgment call. I would probably be inclined to go ahead and increase the amplitude so that I know I'm providing providing the stimulus here, and then take another picture of this, take a screen capture of this, and just say, okay, we've done our pre-calibration into these two different configurations. We know that at least into the resistor pack plugged right into the unit, we have at least something of a cleaner waveform. This is what we're getting into the remote 5 ohms through longer wires, which is maybe more representative of what the UT is going to see. And then you go from here and inject into the UT.
Hey, John.
Yeah.
Some food for thought. Maybe at these speeds, you would be well served to build a load that plugs in instead of your DUT. So you're using the GSE cabling to the box.
Yeah, I mean,
Because it's clear the cabling has a lot to do with it, and the losses and the roll off in the cable.
Yeah.
You might want to make a little, a load that with a connector like your flight unit, your DUT.
Well, I think it's not so much the load, it's the wiring that gets you between the generator and the load.
Yeah. So by doing this, you're plugging in instead of your DUT at the end of your cable, and then you're leveling on that.
Mm-hmm. I mean, yeah, you can always build specialized test equipment. It's just, can you expect the end user to actually do that?
I'm just saying at these speeds, that's the takeaway to me. You may not care at 10 microseconds, but if you're gonna have a requirement levy to test at 150 nanoseconds, these things matter now.
Right. And it gets to be a little less trivial, right? For a 10 microsecond pulse, as we've shown, that's pretty straightforward. You have a dedicated signal generator, and the signal is slow enough that it doesn't really matter up to a point how you make your interconnection, right? You just run a pair of wires from your signal generator to the circuit, and away you go. But this is where you want to make sure, with the project, like, have they actually done their homework to determine that this 150 nanosecond pulse is even realistic?
Yeah, if it's applicable.
Yeah, because I mean, I think it's very interesting that Mil Standard 462 only specifies a 10 microsecond pulse. So like this 150 nanosecond pulse was in there in at least some versions of 461, but it kind of went away. I'm getting the impression not too many people applied it. So So for this project that's requesting to do this, you know, I'm going to be inclined to ask them, you know, is this something you really need, or is this something you're doing just out of heritage or what have you?
Yeah.
But, you know, I'll come back to the basic point that if you've got a power distribution scheme, you know, if your power system architecture is such that you've got a beefy capacitance at the distribution point that's just going to absorb the energy from any of these turn on, turn off transients, all this may go away. All this may be moot. You know, I'll share you know, direct experience here on JWST. When we got to the spacecraft level EMI test, I wanted to characterize the turn on and turn off transients on the power bus as we were turning stuff on and off. And this was not a specific requirement. This was something I specifically wanted to do for engineering data that it took some, you know, a little time just to set up the scope and everything like that, but it was no additional time in the overall scheme of the it's probably the comprehensive performance test at spacecraft level. So we identified a point where we could hook up a scope to the power distribution unit or whatever it was called, and characterize the let me put this back up on the stand here so I can address the audience directly. But if I wanted to characterize what kind of transients were we actually going to see on the power bus as equipment was turning on and off. And I'll start with the turn off transients. You know, I set the scope to trigger, like you have your you know, your 30 volt line, right? When you're fully up and running, the power bus is giving you your 30 volts, give or take, right? And we would expand around, put a DC offset on the scope and expand around it, set the trigger for as low as we could above that 30 volt line with the noise riding on top of it without getting spurious triggers. So maybe a few tenths of a volt above the 30 volts. I never got the scope to trigger once when we were turning any equipment off, not once. So that underscored that the whatever kickback, you know, from turning, you know, inductive kickback from turning equipment off was not an issue. Like their power system also had that, you know, big capacitor bank inside their PDU that absorbed all of that energy from many potential turnoff transients. The turnoff transients just were not an issue. And for the turn on transient, the worst case was pretty sure it was one of the cryocooler boxes. Cryocoolers are very current intensive devices. And I believe the turn on transient magnitude was over 30 amps for about 25 milliseconds. So this wasn't a transient so much as a level shift. It was drawn over 30 amps for about 25 milliseconds, and it pulled the bus voltage down by all of about half a volt for those 25 milliseconds. So had I known that before we were putting all the individual boxes through their test campaigns, I would not have bothered applying CS06. It was not really a worthwhile test for a power system that could absorb those kinds of transients in a pretty benign manner. But certainly turn-offs were absolutely benign. We never had the scope to trigger once. And if the worst case is a 30 amp transient is pulling the bus potential down by half a volt, you know, that seems pretty inconsequential too. So that's where just like doing that upfront homework to understand the power distribution scheme and to determine, are these transients even something that you're likely to be concerned about, can basically render this whole test method rather moot. So so for something like this 150 nanosecond transient that's generating all this rain and all this stuff, I mean, we put some time into understanding the setup just, you know, for the purposes of, well, you know, doing this little demonstration, but also if we end up having to do this for this project. But it's a fair amount of effort that went into trying to understand and deal with this ringing here. for some that may not be even necessary, right? These 150 nanosecond pulses are, I think certainly on the power system architectures that I've described are not going to happen. And it's not time well spent to try to instrument a test like this on something that's just not going to be a concern. At least that's my take on it. But if you think there is enough of a concern to warrant the 10 microsecond pulse, that we've been doing for years, that we know how to do. But again, 30 volts. Look, I've cranked this thing up to 60 volts here to get 30 volts. So there, the reflection seems to be basically cutting the amplitude in half. Sometimes the reflection will double the amplitude, and sometimes it takes away from it. But here again, I mean, these generators are like the default specs in the mill standard are to give you hundreds of volts, and we're generally hanging around about 30 volts. So we're at the low end of the drive capability, and most amplifiers like to be driven near the upper end. Certainly, RF amplifiers like to be driven like pretty close to their capacity, and they're a little bit less. I don't know if stable is the right word, but just you saw that like trying to finesse a level around 30 volts was kind of non-trivial. You get 25 and it jumps up to 31 or what have you. So we're using these signal generators at the low end of their capacity for whatever that's worth. So
Hey, John, if I could add something, my experience with CS06 has not been good, frankly. I was a young engineer building for space station, and our peak voltage, 3 times the bus of 120 is 360. And unfortunately, I had hardware be damaged, which was flight hardware ready to go. It got damaged, and I really learned an expensive lesson that day. So of all the tests, CS06 is the one that really gets my ears up.
yeah, I mean, a lot of people have expressed concerns. I mean, the negative going transient doesn't really seem to pose any real damage concern, right? I mean, you're pulling the bus voltage down to 0 and then it recovers, and if it causes your equipment to be disrupted, generally the worst case is, well, okay, it's disrupted, but it recovers and you get on with life, right? If you find it early enough, maybe you can improve your filtering or what have you. But generally speaking, if it's late in the flow and you see that sort of thing may cause a disruption, may cause your box to reset or whatever, then you can handle that in mission ops, for example, where like, I mean, you generally shouldn't be doing any real critical things while you're cycling power to boxes intentionally, right? But the positive going transient does have some potential stress or damage concerns, right? That if you're going from 30 volts to 60 volts, or even if you're applying a 2 times or 3 times bus potential, you're taking it up to 100 volts. Yeah, that well, it certainly can pose a damage concern, but it's a design driver, right? Those front end components need to be rated or derated to handle that as their maximum potential. That comes up all the time. Where I think when we've gone from like when the default was 28 volts, right? And then we would apply a 28 volt transient. So we're going up to 56 volts. Your front end components, might see 56 volts. But then when we've gone up to 30 and now doubling the bus potential takes us up to 60, I think there have been some cases where that kind of went beyond a threshold. Like some parts were kind of on the hairy edge there. Like they're rated, I don't know, 55 volts or something. Or whatever, somewhere right around 56, 58 volts. And then you're going up to 60 volts. That puts some designers into the realm of, well, my the parts I was planning to use might not be able to withstand that. I might need to go to another class of parts that can withstand 100 volts or whatever. So that sort of thing can be a significant design driver. So you want to make sure that this sort of thing really is necessary, right? If you're applying these pulses that are taking the front end of these power converters up to 100 volts or more, you know, always ask why. You know, is this really something that we should be doing? Is this really a proper concern? And you know, one of my own observations that I will certainly take with me into the next chapter of my life is, you know, as I go into consulting, I fully expect that I might get involved in some more commercial concerns. So that the glimpses that I've had into the commercial world, which are just through talks that I've seen at the EMC symposia and what have you, in a lot of ways, what we do for space applications is a lot easier. That seems a little weird, but now not everything. Obviously, going through parts qualification and all that sort of stuff, you know, people in the commercial world don't have to worry about. But in terms of electromagnetics in particular, there's a lot about space applications that's actually a bit simpler. You know, where we have very specific platforms we're flying on. Like you got a specific, we know what you know what our receiver frequencies are, right? So we know those are the critical frequencies we need to stay away from, and you know we've got defined receive bands that we stay away from, and if we keep any unwanted emissions outside those receive bands, we're good. In the commercial world, you got to stay out of you know a very wide range of frequencies, right? And it's less forgiving. You know, waivers are kind of a way of life for what we do here, you know, in the space community. But my understanding is that they are very, very difficult, if not damn near impossible, to get in the commercial world. Like if you want to sell your product for anybody to buy and use anywhere, you must meet these limits or you will not sell your product. So there's a lot of what we do that actually is a little bit simpler than in the commercial world. So anyway, going off on a little bit of a tangent there, but anybody else have any questions or concerns? That's pretty much what I had to show you here this morning.
I have another comment, I guess, John. This is Ed again, by the way.
Yeah,
I think possible James should measure the inductance of those resistors, so we know when we are at 45 degrees. Since you're not sure.
The load resistors.
Yeah.
Yeah. Yeah, it'd be interesting to put those on an impedance analyzer to see how inductive they
Clearly,
are.
once you hit 45 degrees, you're dealing with a different animal, and you want to know if it's a kilohertz or a megahertz or what.
Yeah. Yeah. Yeah, that's interesting food for thought. So, I mean, this thing, I'm pretty sure is specified to be non-inductive or non-wire wound. I think it says on the website. It doesn't explicitly say on the label here, but you saw that there was still.
It's carbon.
What's that?
It would make sense if it were carbon.
Yeah.
Rather than wire.
But we saw that there was still some ringing just with this sticking right into the, you know, with no lead length, right? Just sticking right into the terminals. So I think what we were seeing just hanging right off of this resistor is pretty close to inherently just what's coming out of the unit. Like that you really can't get better than that. So
agreed.
So the unit is generating some ringing on its own, and it's just made worse when you hang a meter of uncontrolled transmission line over to possibly a wire wound resistor. So, but yeah, all these things to pay attention to, when you're in the lab and you're seeing some strange things, just pay, as we say at BMC, it's all the hidden schematic, right? You think that 5 ohm resistor is just, you draw your little resistor symbol and put 5 ohms on it and you call it a day. But no, there's probably some inductance. We know there's some inductance. It's just how much. If it's a wire wound resistor, that inductance could be pretty significant. And then capacitance between windings and all that sort of stuff. So at higher frequencies, it's not just a 5 ohm resistor anymore. So all these things to pay attention to if you're seeing some strange things. When you're looking at a signal on the scope that doesn't look quite the way you expect it, well, it means you need to adjust your expectations. You need to adjust your model. So. That's all I've got. Anybody else have any questions? Okay. Thank you all very much, and we'll talk to you soon.
Thanks, John.
Thanks, John.
Thank you.
Thanks.
Thanks, John.
You're welcome.